Okay, our second objective is to look at the vulnerabilities in the IEEE 802.11 security. So if you've read this section in the book, you know that IEEE 802.11 is the standard that's used for wireless networks. And so when it comes to computer networking and wireless communications, the IEEE is really the most widely known and really most influential. And that stands for the Institute of Electrical and Electronic Engineers. And they've been around a long time, since 1884, long before the Internet. So when the Internet rolled around and started to go viral in the 80s, the early 80s, the IEEE organization started work on developing some standards that could be used for manufacturers to adhere to make sure that the wireless systems worked and could be counted on. So this additional work that was done by them, and they're not just in information technology, they're across the board, electrical and electronics in general. They called this their Project 802, and it quickly expanded into the many different categories. So that's why you see 802.11a, 802.11n, 802.11b. These are all the different standards that came into play. Now, one of the most well-known IEEE standards is the 802.3, which is this specifications that are used for Ethernet local area networking technologies. So let's talk about a wireless local area network. This was designed to replace or supplement a wired local area network. Wireless technology came along, so IEEE got on the bandwagon to put a standard to that. So it's important to know the history and specifications of the IEEE wireless local area network specs, the hardware that's necessary, and then what we're most interested in, the different types of wireless local area network attacks that can be directed at enterprises and home users. So first of all, what are the different technologies? So again, what we have here is a comparison chart that shows the different technologies, different wireless technologies across a range of attributes. Operating range, operating frequency, is it one-way or two-way communication? What's the data rate or bit rate, and where is it used? What are the potential uses? So if you kind of look at these and take in this table and do comparisons, you can see some patterns developing. Maximum operating range, this is how far these signals propagate. So you can see that the Bluetooth and the Wi-Fi can propagate the farthest in the 100-meter range. That's like over 300 feet. So it's nothing like a long wave or shortwave radio, but it is certainly longer than you would expect for near-field communications and RFID tags. Near-field, of course, has the most limited range. So you don't have to have this table memorized, but it's important to recognize, what the ranges are. For example, to know that the Wi-Fi communication propagates to a much greater distance than does near-field communication. Also, the potential uses row is important to know. Where do we use these? Everybody has a Wi-Fi router at their home. For the most part, that's wireless internet. Bluetooth, communicate between phones, peripheral devices. RFID tag for tracking like an inventory. Near-field communications for contactless pay. So the IEEE wireless local area network specifications, as I just talked about, these folks have been around a long time. They began developing network architecture standards in the 80s. In 97, they released the 802.11, which was clarified in 1999. This then became the standard for wireless local area networks and supported a bandwidth of 2 megabits per second, which turns out to be too slow for most applications. So when you run into a limitation like this, necessity is the mother of invention, as they say. So that spurred on manufacturers to come up with better technology, and that, of course, then led to another standard by the IEEE. So in 1999, they added standards for the 5.5 megabits per second and even almost twice as fast, or is twice as fast, 11 megabits per second under the IEEE 802.11b. So devices that use this experience interference from other products that are in the 2.4 gigahertz band. I mentioned earlier in the previous screencast about how it's possible that your microwave oven can transmit a radio frequency in that same range and interfere with your wireless connectivity. Later in 1999, they added, notice that A came after B. This was introduced, and 802.11a specifies a maximum rate speed of 54 megabits per second, so almost 5 times as fast, using the 5 gigahertz, so doubling this band, the 5 gigahertz radio spectrum frequency. But you'll notice here, you don't get something for nothing. This single range is going to be weaker than the 802.11b. So in 2003, the 11G spec came out, and what it did was is a hybrid. It preserves the stable and widely accepted features of the B at the 2.4 gigahertz range and increases the data rate transfers that we had in the 11A. Remember the 54 megabits per second. So this is gold, right? G, gold. You might think of it that way. It combines the best of the A and the B. So faster speeds and distance coverage of the earlier versions, and overcomes signal attenuation. Attenuation is just a fancy name that means that the signal degrades over time. It's like you only get 1 pip instead of 4 pips at a certain distance. So that's what's with signal attenuation. If you overcome it, then you're going to have 4 pips even at the greater distances. In 2009, the 11N spec came out, and it was ratified and uses both the 2.4 and 5 gigahertz frequencies. So the improvements that we saw here, we're looking at all of these areas that are important to us: the speed, the coverage area, the resistance to interference, and of course security. The data transfer rate gets up to 600 megabits per second in the 802.11n, and it uses these types of antenna devices. Then more recently, in 2014, the 11.11ac was ratified, and it has data rates 6.93 gigabits per second. So this is, if we converted both of these to giga, this would be 6.93, but this would be 0.6 giga. So this is like a factor of 10 improvement. Frequency band that is used is the 5.8 gigahertz. Again, it uses these modulations. So here's a table that compares them all. These are the standards you see across the top. You can see the ratification date in the row in the bottom, and by and large, as we go to the higher letters, if you will, and letter combinations, we're working further into more recent times here. You'll notice also general improvement in all of the categories as we move from left to right. Frequency range kinds of bounces around a little bit between 2.4 and 5 gigahertz, 60 gigahertz for the AD. But the maximum data rate tends to increase as we move to the right. Keep in mind that gigabits per second, 1 gigabit per second is 1,000 megabits per second. Also, you'll notice the range increasing in general as we move to the right, both for indoor and outdoor. So let's look at the hardware that's used for wireless local area networks. They have what are called wireless adapter cards. There's also wireless client network interface / adapter card terminology. This performs the same functions as a wired adapter, and the antenna sends and receives signals through the airwaves. Where would you find this? Well, you would find it typically in your router device, as you can see down here. Where would this be? It's connected with an access point. Again, your router is considered an access point if you have a wireless router at home. So the key to a wireless local area network is this access point. It's centrally located WLAN connection device. So what are the parts of an access point? Just take a look at your router. You'll see these are the various connections that are available on the back of it. There's what looks like a phone socket here. This connects to filter plugs into phone socket. This is a Ready Share USB storage access connection to external flash or pen drives. These are for direct connections, not using wireless, for direct connections into desktop PCs and notebooks. We have the on-off switch for Wi-Fi and the power switch for the router. So those are the key major parts of an access point. It acts as a base station for wireless networks and a bridge between wireless and wired networks. So you might find, if you go look at your router, you might find a computer right next to it, and it would make sense to hardwire that one in because it's in physical proximity to the router. So this is what this would look like on a topology diagram. Here's the internet, and coming into your local network, you'll have a file server, a desktop, and then an access point for your wireless connections. So a wireless local area network using an access point is operating in what's called infrastructure mode. And networks that are not using an access point operate in what's called an ad hoc mode. This is called an IBSS, or Independent Basic Service Set. So this is an interesting situation because with ad hoc mode, devices can only communicate between themselves and can't get outside the network. So that has really kind of limited capability, but it does serve a purpose. There's also, as it says here, there's also a similar technical specification that's been produced by the Wi-Fi Alliance that's called Wi-Fi Direct to handle this type of wireless peer-to-peer communication. So this ad hoc mode is interesting. You should realize that it's there to be useful, to be flexible if you want to quickly and easily set up a wireless network anywhere that users need to share data between themselves but don't need a full-blown internet connection. So an example, one that's given in your book, is when a wireless user might need to send a last-minute document to some associate in a meeting who's sitting across from them at the table. But this is rarely used in practice. Also on the slide, you can see we're talking here about a residential wireless local area network gateway. What is that? Well, this is a device that combines multiple features into a single hardware device. So this would include these things that you see here: an access point, a firewall, a router, dynamic host configuration protocol, otherwise known as a DHCP server, and other features. So these are, if you think about that a minute, you realize that these are residential WLAN gateways, right? That's what we're calling them. And they're entry points for the internet into a wireless network. But you don't see them called that. You don't see them called residential wireless local area network gateway. It's just a wireless router, which you'd find at your home. So let's get to the attacks. What are the various wireless local area network enterprise attacks? Well, it's important to understand kind of the concept here from a security standpoint in a wired world versus a wireless world. In the old wired network that predated the wireless networks we see today, there was a well-defined boundary that you could enforce that protects both the data and the resources. And you can see it here. It's this so-called network hard edge. And typically that was implemented via a firewall. That was our network hard edge. Well, now that we have wireless local area networks in our enterprises, this has really blurred the meaning, in more ways than one, of this kind of hard edge. So now you can see here's the network blurred edge over here in this semicircle that you see. So we still have the internet, obviously, and a firewall for this networked hard edge. But now that we have wireless access points added to the mix, it has blurred the edges that allows potential attackers. You can see two attacker laptops injecting things, basically getting, going behind the scene, so to speak, not going through the front door, but accessing the network through these access points, in effect escaping any security constraints that you might have implemented here in the traditional hard edge. So what are the types of wireless attacks we'll be looking at? We have rogue access points, evil twins, intercepting wireless data, wireless replay attacks, and denial of service attacks. These are the 5 common types of attacks we'll see in wireless networks. So let's look at them one by one. A rogue access point. Rogue. Think about what the name means. Rogue is some type of dishonest or unprincipled person. In this case, it's an access point that we did not authorize but is connected to our network. Maybe it's part of an insider threat. Some disgruntled employee, either knowingly or unknowingly, has attached a device that can then allow an attacker into the network without going through the front-end security. So the definition here, rogue access point, is an unauthorized access point that allows an attacker to bypass network security. So as I said, it could be an insider, most likely, who sets this thing up, and it's behind the firewall. So it defeats the purpose of the firewall by allowing this access. Secondly, we have an evil twin. So you may have run into this, like in an airport or in anywhere where we have public Wi-Fi and people connect to a public Wi-Fi. So if this is the legitimate user, you can see the legitimate AP and the fake AP here. So this is the hacker. He pretends to be the legitimate AP in the hopes that the user will see this Wi-Fi signal and connect to it, thinking that it was the legitimate AP. So you can see the legitimate beacon symbol here in the green, and the fake beacon signals put out by the fake AP in the red. You can see this at airports sometimes, or at the mall. You'll see free Wi-Fi, and perhaps this is a fake AP that's set up to serve as an evil twin. So here's a rogue access point with evil twin attacks. So here's our traditional network, here's our firewall, here's the internet. Here are a couple of legitimate access points, but here's a rogue AP, rogue access point. So we have attackers that can inject behind the firewall through these access points, or through this rogue AP, through this network blurred edge here, we can have an attacker connect. Here's an evil twin over here, so we have legitimate corporate user here thinking they're connecting to one of these access points, but in fact they're connecting to this evil twin that is posing as this access point. Intercepting wireless data, an attacker can pick up an RF signal from an open or misconfigured AP. So it's not necessarily an insider who maliciously sets this up. It could be a misconfigured AP that an attacker connects to. You'd often see this in the past where people would just look for unsecured APs. They'd be driving around in their van in office building parks and so forth, looking for stray wireless signals to connect to. Might be, as innocent as just trying to get free Wi-Fi, or maybe an attempt to penetrate a network. Wireless replay attack. This is also known as hijacking. The attacker captures transmitted wireless data, records it, and then sends it to a recipient without their knowledge. So this could be done with an evil twin AP, and wireless replay attack is just synonymous with the term man-in-the-middle attack. We also have wireless denial of service attack, was discussed in this section. How can you do that? Remember what we mean by a denial of service attack. It means you deprive the rightful user who paid for the service or owns the service from using their information technology resources as they will. How can you do it? Well, number of ways. In the old days, and this predates the information technology revolution, there was RF jamming. If you wanted to disable a radar from a missile site, you would just jam the RF spectrum with electromagnetic radiation to prevent them from using that radar. Well, the same thing is true in our current day and age with wireless networks. If you want to prevent somebody from using their wireless network, you can just intentionally flood the spectrum with enough interference through some kind of transmitter to prevent that device from communicating. There's also spoofing. This is a little more sophisticated than just jamming. Spoofing would be an attacker crafting a fictitious frame that pretends to come from a trusted client when it comes from the attacker. So you're a poser. You're trying to impersonate the legitimate client. And then there's also manipulating duration field values. So this is a little more sophisticated. What's happening here? You can see attackers send a frame with the duration field set to a high value. And what this does is it prevents other devices from transmitting during that period of time. So here you can see an example. Realize, though, when you're doing something like this, a hacker who manipulates duration field values, they're taking advantage of one of the characteristics that's actually an option that's permissible in the 802.11 standard. What we're talking about here is the request to send and the clear to send protocol. So what that does is allows the frames on the transmission to be of a mobile device to be set a certain time frame. So the hacker arbitrarily makes that time frame really long. So essentially what it does is it crowds out the other transmissions. And that, of course, is tantamount to a wireless denial of service attack. So here you can see where that field is in this packet that was captured, presumably from an analyzer like Wireshark. We're actually looking at the byte codes here. And the duration is this second grouping here that you see circumscribed in the blue coloring. Over in the other picture here, you see generating radio frequency interference. This is a AP that's being victimized by this attacker's device that is just broadcasting this burst of RF energy that prevents it from communicating legitimately with this laptop on the network. So if you want to see more information about the duration field, you can visit this hyperlink that's in your PowerPoint. Next, we have wireless home attacks. So what can happen, talking about your home and the network that you have there in your wireless router? Well, the biggest problem here is that most home users fail to configure any security on their home networks. And if you don't have any security at all, then attackers can steal data, read your transmissions, inject malware, force users to download harmful content. So what are the protections for a wireless local area network? Well, the original IEEE 802.11 committee recognized wireless transmissions could be vulnerable. So they took the obvious steps. They started implementing wireless security protocols into the standard. But, and some folks would take exception to this next decision, which was to left it to others to, in this case, the vendors, discretion on how to implement those security protections without actually getting into the weeds. So this is a classic example of where you have a profit motive driving security as well as driving their market share design. So in this case, the security was not necessarily highest on their list. So this meant that protections were vulnerable and led to multiple attacks when they left it up to the vendor's discretion to implement these security protections. So what we came up with, or IEEE came up with, the so-called wired equivalent privacy as a first solution, encryption, using encryption standard as a solution. So WEP stands for wired equivalent privacy. And it is an encryption-based security protocol designed to ensure that only authorized parties can view transmissions. So it uses a secret key that's shared between a wireless client device and the AP. So here's a busy slide that shows how WEP is implemented. So here are the 5 steps, step 1, 2, 3, 4, 5. and you can see that there's a secret key in this part here. There's also something called an initialization vector that you see in step 2. And there's an XOR, exclusive OR calculation, that's done here in step 4. And ultimately in step 5 we have the initialization vector plus the ciphertext that has gone through this process. The other thing here you might not recognize is these two acronyms, CRC and PRNG. CRC stands for Cyclic Redundancy Check. This is a value based on the contents of the text. So Wired Equivalent Privacy calls this the integrity check value, this ICV, and appends it to the end of the text. The other part here, PRNG, this stands for a pseudo-random number generator that is also part of the process in creating this key stream. So together, the initialization vector and the default key are combined to used as a seed for generating the random number here in step 3. So this is the seed right here that goes into the random number generator, so that we can XOR that with the actual plain text and the integrity check value. Okay, so what are the vulnerabilities? This was not a complete solution. As it turns out, it can only use 64 or 128-bit number to encrypt. And of the 64 bits, the initialization vector, that was this first part you see here in step 2, that's only 24 of those bits, so that's kind of short. So the short length makes it easier to break. But more worrisome was that with web encryption, it creates detectable patterns for this IV. This is a big problem and violates the cardinal rule of cryptography to avoid a detectable pattern. So attackers who are just watching this, eavesdropping, could see that IV started repeating after a while. That then led to the biggest problem that was uncovered, and the reason why we had to move away from this first solution here of wired equivalent privacy. So that takes us to the second iteration, which is WPS, or so-called Wi-Fi protected setup. This is an optional means of configuring security on wireless LANs. And it was introduced about 14 years ago in 2006. There are two methods, the pin method and the push button method. So the pin is printed on a sticker on the router or displayed on the wizard if you call up the software. The push button method is you just push the button on the router and it does the security, configuration. So what are the problems with this? Well, there's no lockout time for running the pins, so that allows an attacker to just keep trying, brute force attack. And the last pin character is not part of the pin, it's really only a checksum, so that you're not getting the full usefulness of that length of pin. The wireless router reports the validity of the first and second halves of the pin separately. It is also considered an implementation flaw for Wi-Fi protected setup. Alright, so that takes us to MAC address filtering as another solution. So this is a method of controlling access. And this will limit a device's access to the access point. So here's our access point. Here's a couple of laptops trying to connect to this access point, and you can see the MAC addresses associated with each one. So here's some MAC filtering being used. This MAC address will allow this address, but not this one, is not on the list of permissible MAC addresses. So this is known as, again, MAC address filtering. And it's used by nearly all wireless AP vendors. And it's just a go, no-go list, right? You have to be on the list if you want access to the AP. And I'm talking about the media access control address that is burned in to the network cards on each of these hosts. So what are the vulnerabilities of MAC address filtering? This is unencrypted. That's a big problem. It means attackers can see that and then they can spoof it. In other words, they can substitute it on their own device, create a fake network card with that MAC address on it. Another problem is this can get cumbersome if you have like thousands and thousands of MAC addresses that you have to keep track of. So that's a large number of addresses, can be very challenging. Next we have SSID broadcast. We can authenticate with that. Each device must be authenticated prior to connecting to the wireless local area network. So under open system authentication, a device will discover the wireless network, the SSID, and send association request frame to the AP. So you can see that down here. Here's our client attempting to connect. This is 802.11 authentication open system steps. So we have authentication request sent to the AP. That was this step 1. Next, the frame carries the service set identifier, SSID, that's what that stands for, and device rate information to the AP. SSID is user supplied network name and can be any alphanumeric string 2 to 32 characters long. So the AP will compare the SSID in the frame with the actual SSID of the network. If the two match, then it will authenticate. As you see here in this step 2, it will authenticate and allow the client then to connect to the user in step 3. There's another diagram here that shows the simple authentication. What are the problems with open system authentication? It's weak. It carries only the SSID info, which is based only on a match of that. So this is not necessarily secure, the simple value of the SSID. So the attacker can wait for that to be broadcast, and then they can fashion their own authentication request that includes that. So users can configure APs to prevent beacon frame from including the SSID, but here again the problems. It's only a weak degree of security, can be discovered when transmitted in other frames, so somebody could eavesdrop and get it. And older versions of Windows, like XP, which is no longer, that's reached end of life, have an added vulnerability if you're using this approach. So WEP is 802.11 security protocol. It encrypts plain text into ciphertext. The secret key is shared between wireless client device and the access point, and the key is used to encrypt and decrypt packets. What were the vulnerabilities with WEP? It can only use the 64-bit or 128-bit number to encrypt. The initialization vector is only 24, and the short length makes it easier to break. So this is a summary of what we saw in the previous slide as to the vulnerabilities of wired equivalent privacy. So SSID broadcasting security issues. So these are the potential problems with using SSID broadcasting. Some wireless security sources encourage users to configure their APs to prevent the broadcast of the SSID. That's the beaconing aspect of SSID. That's not a complete solution either. It has limitations, as it says here in these 3 subsidiary bullets. Why? Because it can be discovered, because it's transmitted in other frames. It's not secure. And it may prevent users from being able to freely roam from one AP coverage area to another, and it's not always possible to turn it off. So let's look at a summary. We're going to summarize several of the wireless protections that were vulnerable and led to multiple attacks. Here are the vulnerabilities. They can be attributed to these older technologies, WEP, WPS, MAC filtering, and SSID broadcasting. So we needed, they were all addressing an individual problem. So we needed kind of a one-size-fits-all unified approach. And so that's when we get the motivation for the standards that we have today, which would be the 802.11i and the WPA and WPA2, which are the primary wireless security solutions in use now. So let's look at WPA. This was introduced in 2003 by the Wi-Fi Alliance, and its design goals to fit into the engine, the existing engine. They didn't want to have to require new hardware for it, so it had to be backward compatible with existing hardware. So this is a subset of the 802.11i, and there's 2 modes, personal and enterprise. It uses Temporal Key Integrity Protocol Encryption, or TKIP, and it is the heart of the security solution in WPA. It functions as a wrapper by adding an additional layer of security. Remember we talked earlier in the cryptographic section about how the longer the key, the more bits, the more secure. Well, this uses a longer 128-bit key, which is longer than the wired equivalent privacy. Has a unique base key that's created for each device using a master key. So you can see another principle of encryption in here. This looks like asymmetric cryptography. Dynamically generated keys for each new packet, and includes this all-important MIC, or message integrity check, which is designed to prevent man-in-the-middle attacks or foil them. There's also pre-shared key authentication. This is authentication for WPA personal. It's accomplished by using a pre-shared key. So here's the way it works. After the AP is configured, the client device must have the same key value entered. The key is shared prior to communication even taking place. If you're in a bar, or like it says here, a cafe bar, where you don't have authentication, they use what's called the open method, where you use a passphrase to generate an encryption key. So that must be entered on each AP and wireless device in advance. And devices that have the secret key are automatically authenticated by the AP. So what are the vulnerabilities with WPA? Key management. Remember we talked about key management being a problem in asymmetric cryptography. So if we start adopting that approach here, we got that same problem. So key sharing is done manually without security protection. Keys are going to have to be changed. You got to keep them secret. They can't be disclosed to guest users, and when guest leaves, they need to be changed. Passphrases are subject to cracking. They're 8 to 63 characters. If you have 20 or less, that's going to be vulnerable. So they came up with the second generation of WPA, and this is likely what you have on your home router, WPA2. This was introduced in 2004. It's based on the 802.11i standard. It has two modes, as before, personal and enterprise. So WPA2 allows wireless clients to use the temporal key to operate in the same WLAN, whereas the 802.11i does not permit them to do that. There are two major security areas, encryption and authentication. So let's look at some of these. We have AES CCMP encryption. Remember we talked about AES, that's the Advanced Encryption Standard Block Cipher. Talked about that back in cryptography. That's what's used by WPA2. It performs, if you remember, it performs 3 steps on every block. That's 128 bits of plain text, and within the second step they do multiple iterations where bytes are substituted and rearranged. So with counter, this is the CCMP part, with counter mode with cipher block chaining message authentication code protocol. So that's a huge mouthful. CCMP. Just remember that it is an encryption protocol used for WPA2, and it specifies this use of CCM with AES. It provides the cipher block chaining message authentication code, CBC-MAC component, provides data integrity and authentication. So this is like an alphabet mix. What I would recommend that you do is, when you're studying this for the certification exam, is you create a table where you list these things together and just know what the name of it is. You don't have to go into the details of this, the nitty-gritty details of how this cipher works, but you do need to know what it brings to the table. In this case, it provides data integrity and authentication. So CCMP and TKIP both use a 28-bit key for encryption, and this MIC that we were talking about on the last slide, this message integrity check value. So let's talk about IEEE 802.1x authentication. This is a new standard, 802.1x. This is now an authentication piece that's been inserted into the WPA2 enterprise model. It's originally developed for wired networks, but this now provides a greater degree of security by implementing, and this is the key part, port-based authentication. port-based. You see the X? You should be thinking port-based authentication. Blocks all traffic on a port-by-port basis until the client is authenticated. So clients are blocked from received traffic before they're authenticated. So here you see the process for the 802.1x authentication. So here are the players. We have the supplicant. This is like the client trying to gain access to the network. Then this is like the bouncer at the bar, the authenticator, to serve as go-between with the supplicant and the resource, whatever they're trying to get to. But the authenticator also has at its disposal the authentication server, which has the database that determines whether or not this supplicant is legitimate. So step 1, supplicant asks to join the network. The authenticator asks the supplicant to verify identity. Supplicant sends their credentials. Okay, now that the authenticator has the credentials, it goes off and says, okay, is this guy for real? And then the authentication server checks it against the records and says yay or nay, whether or not they're legitimate. And then finally, if approved, the authenticator would send the approval back to the supplicant to join the network. So the point here, port by port, and clients are blocked from receiving traffic before they're authenticated. So it's important that communication between the supplicant authenticator and authentication server is secure, that whole path that we saw in the last slide. So how do we secure this communication? We use EAP, Extensible Authentication Protocol. It's a framework for transporting the authentication protocol. So we have a protocol to do another protocol. This is an extensible authentication protocol. So it defines the message format on how these messages are to be formatted and constructed. They take one of 4 types. They can come in 4 different versions, I should say, 4 different types of packets. It can be a request, a response, a success, or failure. And if you go back here, you can take a look at each one of these and determine which of those 4 categories it would fall into. So a common EAP protocol is the so-called PEEP, Protected EAP, and this simplifies deployment of the 802.1x by Windows logins and passwords. It basically creates an encrypted channel between the client and authentication server for the PEEP. Lastly, for this objective, there are several EAP protocols that are supported for the enterprise version of WPA2, and these are the most common ones. Again, this is the kind of table that you would want to put together to use to keep these all straight. So the thing that's common amongst these, of course, is authentication protocol, the EAP, DAP, or EAP. And then in the description you can see, what other security application you're bringing to bear on it. So in this case, it's TLS, Transport Layer Security. So that concludes the discussion on the second objective, which is dealing with the IEEE 802.11 security and vulnerabilities. Lastly, we'll look at securing network wireless.